So far, we've talked about the sums of finite geometric series, where we are adding up things to a specific number of terms. But what if we were to add up these terms forever? What if we were going to continue to sum these terms in a sequence over and over and over, and it were just to never stop being added up? We call that an infinite. We call that an infinite geometric series, and they're quite different because we're adding up things forever. And before you think that this is never going to work out, and how can we add an infinite number of numbers, just you wait, because we can actually do this sometimes. So consider for me what happens in this equation. This is our general equation for an infinite series, a geometric series, the sum of an infinite geometric series. What happens as this n value gets really, really large? So we're blowing up n because n is going on forever and ever and ever. Well, that's not really going to affect most of the things in this. U sub 1 doesn't change, 1 doesn't change, r doesn't change. But what's going to happen is this r to the n power is going to be greatly affected by whatever that exponent is. So if the absolute value of r is greater than 1, meaning I'm dealing with numbers like 2, 3, 4, 5, or negative 2, negative 3, negative 4, negative 5, what's going to happen is the series diverges. That's kind of a key term. It's a divergent series, or it diverges. It becomes infinitely large. So think about what that means. Here is an example. If I took this series and I took it out to n would be a really, 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 really large number, this 2 to the n power just kind of explodes. It blows up. It becomes very huge. And as I'm adding up these terms, it's not really going to converge to any certain number. So think about the picture that I have coming up here, where I've actually graphed the sum of these terms up for n number of terms. So what's going on here in the bottom is my terms are going up. So when I add up the first term, I get, looks like a 1. The second, when I add up the first and second, it's 3. First, second, and third, it's another term. And as I add these terms up, since 2 to the n becomes really, really huge, this sum just kind of goes off the charts. And this is going to keep spiking upwards, much like an exponential would. So I can't actually find what the sum is of this infinitely large geometric series because this r value is greater than 1. But what about if r is less than 1, or the absolute value is less than 1? Things like a half, or negative a half, or positive a third, or negative 0.12345. What happens when n gets very large in this case? Well, think about what happens to r to the n. If I were to take something like 1/2 and raise it to a very large number, this is going to approach 0. It gets really, 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 really small. So when n becomes very large, this r to the n really approaches 0, and it almost becomes insignificant completely. So let's see what I mean when I say that. If I take s sub n and I'm trying to find what the value or the sum of this series is that goes out infinitely, I'm adding up an infinite number of terms in this series, I would plug it into my formula just like I have before. But now when n becomes really big, it's kind of like this becomes one big fat 0. And my formula becomes 1 times 1 over 1 minus 1/2. So I'll let you figure out what that should actually equal, 1 divided by 1 minus 1/2. And as you ponder that, take a look at this graph that shows the sum of the series as n gets really, really large. So as I'm adding up these terms, what's going on is I'm adding smaller and smaller and smaller and more insignificant values to this series. And what we'd say is that this sum converges to a specific value. And it's all because this becomes really close to 0. So it's kind of like it's not even important. It's such a negligible amount that it's almost like it doesn't matter. It's not even there. So if you actually figured out what 1 over 1/2 is, that is equal to 2, and look where this series converges. It converges at 2. When I add up a series that follows this sort of a procedure, it actually equals 2 if I were to add this up infinitely on and on and on and on forever. So we can actually find these infinite series sums as long as the absolute value of r is less than 1. So if I were to take this out further, like I said before in the last example or in the last slide, this becomes 1 over 1 minus 1/2, and this works out nicely. So in general, if I want to generalize this for what we call a limiting sum, it's a limiting sum because it has a limit to it. It does not diverge and continue forever to spike towards infinity, but the actual sum limits at a certain point and has a ceiling to that, like the Desmos graph from the last example. And here's my equation for a limiting sum infinite geometric series. So notice there's no n here because this is after adding up an infinite number of terms. So I'm not stopping n at any point. This is what I would get once I would add all of the terms for infinity into this series. So this is my general formula for what we call a limiting sum. So let's see this put in practice here. I want to write this decimal, 0.7, repeating as a rational number. So we might think like, well, how does this have anything to do with an infinite geometric series? Well, let's think about this. The first term, or what I can write is that this is basically essentially 0.7777 on and on and on. I can write this as the sum 0.7 plus 0.07 plus 0.007 and so on and so forth. So what I'm doing is I'm separating out all the digits or all the decimal places of this number, and now I can express it as this series of terms being added up together. So hopefully that kind of makes some sense. If I add 0.7 plus 0.07 plus 0.007 and do that, keep that pattern up forever, I'm going to get 7 repeating. And what I have here is a geometric series. Hopefully we can see that here's the first term, u sub 1, and the ratio, or the factor that separates all of these terms, is basically multiplying by 1/10. If I take 0.7 and multiply it by 1/10, I get 0.07. If I take 0.07, I multiply that by 1/10, I get 0.007. So what I have here now is I have a u sub 1, 0.7, and I have an r. That's 1/10. So I can use my limiting sum equation for my infinite geometric series, since this r, notice, is less than 1, so that works. And that sum should be equal to, what do we say, u sub 1 over 1 minus r. Over 1 minus r. So now we're just plugging stuff in. So s is going to equal 0.7 over 1 minus 1/10. And I can simplify this to be 0.7 over 1 minus 1/10 is 9/10, or 0.9. And we don't like these decimals in the fractions like this, so I can just multiply top and bottom by 10 to get rid of these decimal places, and this is actually equal to 7/9. So we can verify this. If I type 7/9 into my calculator, I should get 0.777777. And sure enough, let's try that. 7 divided by 9. That is 0.777. Now what's going on with that 8? That's the calculator trying to round this at a certain point. So really, this does continue on forever. So we're good there. Why don't you try an example that's just like it here? Now I have 0.4 repeating. So expand this out as a geometric series. Give this one a shot. Pause the video, and we'll see how it goes. Okay, so here is my workings out for this one. You'll notice that in this example, or my work here, I wrote this not as 0.4 but 4/10, and not 0.04 but 4/100, just to see that we can express this in two different ways. And we come up with 4/9 as the rational number that expresses 0.4 repeating.